Hello everyone, welcome back to the channel. Today I'm going to show you how to make a solar weather station. Once we finish this project, it's going to look like this. It displays data like expected power production from my solar array, outside air temperature, shaded air temperature, whether it's raining or not, how hard it's raining, and even solar irradiance. The best part is that the estimated power production matches up really well with my actual power production. This whole idea started when I was looking at solar irradiance meters. They were super expensive and none of them could integrate within my home assistant setup. So I started thinking, is there a cheaper way to do this? That's when I asked ChatGPT if it had any ideas. It suggested the BH1750 sensor, which costs just $6. I've used the BH1750 before in an automatic outdoor lighting project, but I didn't know it could measure solar irradiance too. I found the cheapest one on Flarobo for just 81 rupees, which is around $1 according to Google. I'll put all the buying links in the description below. Now let's talk about the components we'll use. First, we have the ESP8266 node MCU, which will control the entire setup. Next is the BH1750 lux sensor, which we'll use to measure sunlight intensity. We'll also use a BMP280 sensor for temperature and pressure, a rain sensor to detect rainfall, and a DS18B 20 temperature probe for additional temperature measurements. Everything will be integrated into Home Assistant using ESP Home. This is the circuit diagram of the station we are making. You can solder the parts to PCB or connect with the jumper wire as shown here in this diagram. This diagram is also available for download. You can check description for link. So, as you can see, I've soldered all the components to a PCB along with the ESP8266. If you're not comfortable with soldering, don't worry. These parts can also be connected using jumper wires. I haven't soldered the BH1750 light sensor directly to the PCB. Instead, I used some 15 cm wires to connect it. This is because the BH1750 will be permanently glued to the lid of my project box, as you'll see later in the video. Now this module you're seeing here is a buck converter. It has selectable voltage and can take input up to 15 volts. Now that our circuit is ready, we need to connect it to the ESP Home dashboard through USB. Connect the ESP to the device running Home Assistant using a USB cable, and then we'll get started with the configuration. Once you've connected the ESP to Home Assistant, go to ESP Home and click on New Device. Name the device whatever you want. I was thinking of naming it Weather Station, but I already have an older weather station named Weather Station. So I'll name this one Solar Station. Click Next and select the ESP if you're using it. Otherwise, select the board you're working with. After that, click Install and choose the installation method. Since I'm connecting directly, I'll select Plug into this device running ESP Home. If you're not connected to the Home Assistant server directly, you can choose another method. After the installation, click Edit on the device we just installed and you'll see this page. Now I'll show you an easy way to create the YAML configuration for ESP Home. If you've copied my circuit diagram and everything else, you can skip this part and just copy my code from the description. But if you're making your own custom sensor setup, stick around and follow these steps. Here we are on the ESP homepage for the BH1750 sensor. Since it works with I2C, the first thing we need to do is set up I2C. Just copy the I2C configuration example from the page and paste it into your YAML file. Now, change the SDA pin to 5 and the SCL pin to 4 or whatever pins you've used in your setup. Next, go back to the BH1750 page and copy the example configuration for the sensor. Paste it into your YAML file. You can use the default example if you want, but you can also add more options or edit it. I'll show you how to edit it by changing the name. Here, I'll rename it to Solar Power, but then I'll change the update frequency to 5 seconds. Now let's move on to the BMP280 sensor. Go to the ESP homepage for the BMP280, copy the I2C example configuration and paste it into the YAML file. We don't need to set up I2C again because we already did that for the previous sensor. and both sensors are on the same bus. Just edit the BMP280 YAML configuration as you wish. Finally, do the same for the rest of the sensors. I'll fast forward the video from here to save time. If you have any doubts regarding any of the sensor configuration or anything else regarding this project, try asking it in comments. I will try my best to help you. After you're done copying my YAML file or writing your own, the next step is to save and upload it to the ESP. Simply click Save and then install. I'll install it wirelessly this time since we've already uploaded the firmware to the ESP once using the USB. Now, we can use an OTA update, which means updating via wireless to upload or modify the configuration on the ESP. After we're done uploading, you can view the logs from all our sensors. Here you can check if they're reading the correct values, if any values seem unusual, or if any sensors are showing errors. As you can see, we've got an error on our BMP280 sensor because it has failed. This usually happens when the I2C address we've entered in the configuration is incorrect. You just need to find the correct address, which will be displayed in the logs. As you can see here, we're off by 1 digit. To fix this, simply go back to the configuration and update the sensor address to the correct one shown in the logs. After updating, re-upload the configuration and it will be fixed. Now let's get back to the hardware real quick. I've installed this circuit in a project box with a hole on its lid for our light sensor. Then I hot glued a thin layer of glass on top of the hole to protect the sensor. You can design your enclosure however you like. It's not necessary to copy mine exactly. After securing the lid with screws and organizing the wires, I covered the top layer of the box with aluminum tape. This helps make it more weatherproof. Now, let's finish the rest of the configuration with Home Assistant. Go to the Devices and Services section, then to the Integrations tab in Home Assistant. You'll see the solar station automatically discovered there. Click the Add button to start the setup and then click Submit. And just like that, your ESP Home solar station will be fully configured. You can view all its settings right there. But we're not done yet. As I mentioned at the start of the video, this station will show you the estimated solar power production and the watts per square meter value. Right now, it's not displaying those, so let's configure them. So here is the updated YAML configuration for the solar station. As you can see, I've made some changes compared to the initial YAML file. I've also completed the rain sensor ADC configuration so that it displays the rain value in percentage instead of volts. You can notice the green comment I've added to indicate where this change has been made. If you're using a different ADC rain sensor, you can modify this section accordingly. Now we come to the main part of this video, how to configure a cheap $1 sensor to work like a $400 Irradiance meter. Here you can see my template sensor that performs this task. The only adjustment you might need to make is to tweak the lux per watt per square meter value if your sensor readings are way off. Simply increase or decrease this value and then check if it helps. I got my current value from a website that I'm showing you now. It states that 118,000 lux equals to 1000 watts per square meter. You can use this as a starting point and see if it works for you. The second template sensor converts the solar irradiance we calculated earlier into an estimate power production value. For this, you just need to input the total wattage of solar panels you've installed. As you can see, I've entered 1600 watts, which is the capacity of my solar panels. Finally, here are my two graphs. The first graph shows the estimated production, which comes from the station we just built. The second graph shows the actual solar production from my solar panels. You can see how accurate the results are. The scaling of the graphs is slightly off, which makes them look different. But if you compare the fluctuations in estimation and actual production, they match exactly. Now your weather station is complete and you can enjoy using it. Before you install it, just keep in mind that the angle at which you mount your light sensor should match the actual angle of your solar panel, which you have mounted your solar panels on any structure. Should match the actual angle. This ensures that everything will work as it should and the reading will be correct. And here you can see it in action. Thanks for watching. See you in the next video. Bye.